So in this video I'm going to discuss the problem in thermal and statistical physics which appeared in JEST Physical Science 2016 examination. So let's take a look at the problem first. The statement is an ideal gas with adiabatic exponent gamma undergoes a process in which pressure P is related to the volume by the relationship. So we are given a relationship here which connects the pressure with the volume P equal to P naught minus alpha times V. So let's call this as equation 1. Okay. So here P naught and alpha, these are given to be positive constant. These are positive constant. Okay. Let's call this equation A. The volume starts from being very close to 0 and increases monotonically to P naught by alpha. Okay. At what value of volume during the process does the gas have maximum entropy? So that means volume is going to change from a value that's very close to 0 to a certain value P naught by alpha, and we have to find the value of volume for which the entropy it's going to maximum. So that means here the variable is volume, so that means we have to make use of the condition that ds by dv, that change in entropy with change in volume, that is equal to 0. So we will make use of this result. Okay, so now the point is how we can solve this problem. Okay, so we are going to make use of the TDS equation. Okay, the TDS equation is TDS that is equal to N CB dt plus PdV. Okay, or this can be further rewritten as TDS. I'm going to replace CB with R upon gamma minus 1. So N R upon gamma minus 1 dt plus PdV plus PdV. So I'm calling this equation 1. So here we have made use of the fact that CB that is equal to R upon gamma minus 1. Okay. Now for an ideal gas, we know that for an ideal gas the equation of state is PV that is equal to nRT. Okay, or I can write P dV plus V dP that is equal to nR dt. Okay, so here I'm going to replace nr in equation 1 with this expression here. Okay, so let's see. So let me call this as equation 2. Okay, so that 1 and 2 implies that 1 and 2 implies that TDS is equal to, so I'm going to replace nRdt in equation 1 with this expression. Okay, so PdV plus VdP upon gamma minus 1. Okay, so I have replaced this nRdt with here in equation 1, and now plus PdV, the last term PdV. Okay, now by making the same relationship, if we mean from here, from the equation of state, T is equal to PV upon nR. Okay, so I'm going to replace this T with PV upon nR, that is PV upon nR ds that is equal to PdV upon gamma minus 1, and then I am writing the last term here. I am rewriting this expression basically P dV, and then the second term from here plus B dP V dP upon gamma minus 1. The only purpose of doing this step is so that I want to separate the terms having dV and dP. Okay, and this is equal to PdV outside PdV upon 1 upon gamma minus 1 plus 1 plus V dP upon gamma minus 1, and this upon for the solving this, Pb upon nr ds, that is equal to gamma over gamma minus 1 Pdv plus Bdp plus Bdp upon gamma minus 1, that is the equation 3. Okay, now we are given that now P, that is equal to P naught minus alpha V, that's given to us. Okay, so that means dP is equal to minus alpha times dB. So the equation 3 and 4, that is equation 3 and equation 4. What is equation 4? So I'm calling this as equation 4. So that 3 and 4 implies, so I'm going to make use of the value of dP as minus alpha dB in equation 3. So that equation 3 reduces to Pb upon nr ds, that is equal to gamma upon gamma minus 1 Pdv minus, it's the value of dP, okay, minus alpha b upon gamma minus 1 dB. Okay, so that from here, after rearranging the terms, I'm writing ds by dB. Okay, so I will take the constant term on the other side, so that is equal to gamma upon gamma minus 1, gamma upon gamma minus 1, and then nrp upon Pb minus alpha nr upon gamma minus 1 alpha nrb upon Pb, something like this. Okay, now for entropy to be maximum, for entropy, so let me call this as equation 5. For entropy to be maximum, ds by dV equal to 0. So this implies, because here in equation 5 the denominator is same in both terms, so therefore this implies ds by dV, that is equal to 0. So that means gamma time nrp minus alpha nrb, that is equal to 0. Okay, or because nr is common, so we can take nr outside, so that is, this implies nr into gamma p minus alpha v, that is equal to 0. Okay, or from here we conclude that alpha p, that is gamma p, that is equal to alpha times b. Okay, so now here again we will make use of value of p that's given to us here, which we called as equation A. Okay, so we are going to replace p with, so gamma times p, which is p naught minus alpha v, that is equal to alpha times b. Okay, or gamma p naught minus alpha gamma v, that is equal to alpha times b. Okay, and this upon further arrangements, alpha v plus alpha gamma b, that is equal to gamma time p naught. Okay, so v into, or alpha v into 1 plus gamma, that is equal to gamma times p naught, or from here we notice that v, that is equal to gamma p naught upon alpha into 1 plus gamma. So this is the value of the volume for which the entropy will have a maximum value. Okay, so let's see. So this is gamma times p naught upon alpha, gamma p naught upon alpha into 1 plus gamma. So therefore option C is the correct option here. So let's continue with the next problem. The statement is, a gas of n molecules of mass m is confined in a cube of volume V equal to L cube at temperature T. The box is in a uniform gravitational field minus Gz. Assume that the potential energy of a molecule is U is equal to mgz, where Z ranges from 0 to L, is the vertical coordinate inside the box. The pressure Pz at a height Z is, okay. So we can solve this problem by making use of the partition function approach, okay. So here the Hamiltonian for the particle that's given by the Hamiltonian of the system, you can say that is equal to px square plus py square plus pz square upon 2m. That's the kinetic energy of the particle in 3 dimension, plus the potential energy, that is mg z, where z can range from 0 to L, okay. So once the Hamiltonian of the system is recognized, then we can write the partition function, okay. So the partition function is Zn for n particles, Zn, that is equal to 1 upon h power 3n, okay. And then okay, since it's not given that what kind of gas molecule they are, but in principle we consider the gas molecule to be identical, okay. So that's indistinguishable, so then we can carry a factor of n factorial here also, okay. And then it's the integral minus infinity to infinity exponential minus px square upon 2m kt, and then dpx, the integral corresponding to the motion along y direction, exponential minus py square upon 2m kt dp by exponential minus pz square upon 2m kt dpz, and then integral over space coordinates, that's x and y. So I'm writing them together, dx dy, and here the limit of integration, they will range from 0 to L. And then along the z direction 0 to L, and exponential minus mg z upon kt and then dz, okay. And because we are having n particle system, so power n basically, okay. So here in order to solve these integral, we will make use of the some of the standard integral and results, minus infinity to infinity exponential minus alpha x square dx, where alpha is a constant and that is equal to under root pi by alpha, okay. So these first three integrals, they can be solved directly by making use of this standard results, and each of these integral, for example exponential minus px square upon 2m kt dpx from minus infinity to infinity. So here alpha is equal to 1 upon 2m kt, k is the Boltzmann constant, 2m kt, so that under root pi by alpha becomes under root pi by alpha is 2 pi m kt under root, okay. So therefore the partition function reduces to 1 upon n factorial h power 3n, and then inside the bracket we will have 2 pi m kt, it's under root pi by alpha for here, and 1 by 2 for one integral, because we are having three such identical integral, so power 3 by 2, okay. So these three integrals, they will contribute, they will have this contribution, okay. And when we will perform the integration over the space coordinate along x and y direction, so this will give us a factor of L square, okay. Now the last integral, so this is equal to exponential minus mg z upon kt divided by minus mg upon kt, and limit of integration, the limits are 0 to L, okay. And this is equal to upon solving this, we will obtain this is 1 upon n factorial h power 3n into 2 pi mkt power 3 by 2 and then L square and then minus kt by mg minus kt upon mg and then upper limit. So for upper limit will give us exponential minus mg L upon kt minus lower limit, that will give us a factor of minus 1, okay, and its power n. Okay, now this can be further solved as, so Zn, that is equal to 1 upon n factorial h power 3n and inside the bracket it is 2 pi m kt power 3 by 2 L cube kt upon mgl. So here I have divided and multiplied, I have multiplied both numerator as well as denominator with L. So we have done it intentionally to bring volume into the picture. Okay, so and then multiply by 1 minus exponential minus mgl upon kt and its power n. Okay, so this turns out to be equal to 1 by n factorial into 2 pi m kt upon h square and its power 3n by 2. So these terms, this is merely a rearrangement of the terms, and then multiply by kt b. So I am replacing L cube with b, kt b upon mgl its power n, okay, and then 1 minus exponential minus mgl upon kt its power n. So this can be further rewritten as, so this is equal to some constant term c1 and then b power n. Here I have clubbed all the terms in c1, all except b power n from here. Okay, so I'm doing it intentionally because ultimately I'm looking for the expression for the pressure which require only the dependence on the v by keeping rest of the parameters constant. Okay, so that's the partition function where c1 includes all other parameter here. Okay, so let me call this as equation. So I haven't given any yes 1, and let me call this as equation 2. Okay, so now the Helmholtz free energy F, that is equal to minus kVt ln Zn. So that is equal to minus kVt ln c1 b power n. Okay, now the pressure is connected with the Helmholtz energy by the relationship minus dF by dV by keeping rest of the parameters constant. So that is equal to minus curly b of minus kVt ln c1 b power n. Okay, so minus will become plus, so that is equal to kVt. Note that here k, wherever I have written, it is Boltzmann constant in principle. Okay, so kVt and then its differential with respect to b, so that is 1 upon c1 b power n. Okay, and then the differential again the differential, that's c1 as it is, and then n b power n minus 1. So b power this will be b power n minus 1. Okay, so that is equal to, so c1 and c1 they will cancel with each other, so this is equal to n kVt divided by b power n multiply by b power n upon b. So this will cancel with this one. So that P, or the pressure expression for the pressure, that is equal to n kVt upon V. Okay, so let's see. So therefore the C is the correct option here. Okay, so let's continue with the next problem. The statement is, a two-dimensional box in a uniform magnetic field B contains n by 2 localized spin-half particle with magnetic moment mu and n by 2 free spinless particle which do not interact with each other. The average energy of the system at temperature T is how much? Okay, so we are having a system which comprises two different kinds of particles. Okay, the first kind of particle, they are n by 2 spinless free particle. Okay, which do not interact. Okay, and it's they are confined in two dimension, please note it. Okay, and the second set consists of n by 2 spin half particles with moment mu, Okay, now let's try to figure out the average energy associated with the first case. Okay, so case 1, that is n by 2 free particles in two dimension. Okay, so let's see. So if we are having a free particle in two dimension, okay, so that means it can only move in x and y plane. Okay, let's say only in x and y plane. Okay, so the it's the Hamiltonian, so because it's a freely moving particle, so its energy, the corresponding Hamiltonian will be of this type, px square plus py square by 2m. So that means the corresponding translational degrees of freedom, they are 2, because it's a two-dimensional motion. So only 2 degrees of freedom, 2 translational degrees of freedom. Okay, so therefore the average energy per particle in two dimension. Okay, so that is equal to, let's call this as average energy per particle, let me call this as E1. Okay, and that is equal to the degrees of freedom 2 and then the average contribution from 1 degree of freedom, which is half kVt. This is from equipartition theorem. Okay, so that means the average contribution per particle, it is kVt. Okay, so therefore average energy with n by 2 free particles, that will be equal to the number of particles multiply by average contribution from each particle, that's kVt. Okay, so let's call this as our result 1. Okay, now we are done with the case 1. Now let's see what is the average energy content associated with n by 2 spin half particles. That's a case 2. Okay, in case 2 we are having n by 2 spin half particle in magnetic field B. Okay, so now each spin, it's having two different options. Okay, so the first one is either it can align along the field direction so that the corresponding interaction energy is E1, let's call that is minus mu dot B when spin is along the field. First spin along field direction. Okay, that's the interaction energy. And the second option is when spin is aligned opposite to the field direction, so that mu and B, they are having an angle of 180 degree. So that minus mu dot B, that is equal to minus mu B cos 180 degree, and that will give you interaction energy of mu B. when spin opposite to B. So that means we are having two energy orientation. So one is E1 and second one is E2 with the value of minus mu B and mu B. Okay, so that the partition function for a single spin system is Z1, that is equal to exponential minus beta E1 exponential minus beta E1 plus exponential minus beta E2, and that is equal to exponential beta mu B plus exponential minus beta mu B. Okay, so that the average energy that can be quickly calculated. So this is equal to 2 cos hyperbolic mu B by kt, or beta mu B, you can say mu B upon kt. Okay, so let's call this as equation 2. So from here the average energy per spin that can be calculated. So average energy per spin, let me call that as E1 prime, that's the average energy per spin, that is equal to minus curly beta of ln z1, and that is equal to minus curly beta of ln of 2 cos hyperbolic mu B upon kt. Okay, so let's move to the next page. So that the average energy, that is E1 prime, that's the average energy per spin, that is equal to minus 1 upon 2 cos hyperbolic mu B by kt. Okay, and then again its differential, that is 2 sin hyperbolic mu B by kt, and then again the differential of mu B by kt with respect to beta, so that is equal to again that will give us a mu multiplied by magnetic field B. Okay, so that the average energy it comes out to be equal to, so we are having an active sign here, that is equal to minus mu B, and then 2 will cancel with 2, it's sine over cos, so that is tan hyperbolic mu B upon kt. Okay, so let's call this as equation 3. Okay, yes, this is equation 3. So this is the average energy per spin. So the energy for the, how many spins do we have? It's n by 2. Okay, so for the n by 2 spins the average energy will be, let's call that as u1 prime, so that is equal to, for n by 2 spins it's n by 2 multiplied by average energy per spin. Okay, so that is equal to minus n by 2 mu B tan hyperbolic mu B upon kBt. That's equation 4. Now the total energy of the system, the total energy of system constituting n by 2 spin half particle and n by 2 spinless particle, so that is equal to U total, that is equal to, so now it is the average energy with n by 2 free particle. It's equation, it is the sum of equation 1 and equation 4. Okay, so that is equation 1 gives us energy of n by 2 kVt, and then minus n by 2 mu B tan hyperbolic mu B upon kt. So that's the answer. So therefore option C is the correct one here in this case. So let's continue with the next problem. The statement is, for a quantum mechanical harmonic oscillator with energies En is equal to n plus half h cut omega, where n is equal to 0, 1, 2, the partition function is. Okay, so we are given the energy spectra of the harmonic oscillator. The energy spectrum of harmonic oscillator is given by En, that is equal to n plus half h cut omega, where n is equal to 0, 1, 2 and so on. Okay, the corresponding partition function is q, that is equal to summation n taking value from 0 to infinity exponential minus beta En, and that is equal to exponential n taking value from 0 to infinity exponential minus beta into n plus half h cut omega. Okay, now this is further equal to, we are going to assign the value for n. So if n is equal to 0, we will have exponential minus beta h cut omega by 2, and then when n is equal to 1, so 1 plus 1 by 2, that will give us 3 by 2. So that the second term will be exponential minus 3 by 2 beta h cut omega plus exponential minus 5 by 2 beta h cut omega plus so on. Okay, and this is equal to exponential minus beta h cut omega by 2 into 1 plus exponential minus beta h cut omega plus exponential minus 2 beta h cut omega plus so on. Okay, so this is further equal, this is of the type a plus ar plus ar square, where r is equal to, that is the common ratio, is equal to exponential minus beta h cut omega. Okay, so this can be written as q, the partition functions, that is equal to exponential minus beta h cut omega, okay, by 2 outside, and then a over 1 minus r, a upon 1 minus common ratio, that is exponential minus beta h cut omega minus beta h cut omega. Okay, so this is further equal to, if we okay, if we take exponential this minus beta h cut omega outside, so that this can be further rewritten as exponential minus beta h cut omega by 2. Okay, so what I'm doing is I'm taking this exponential minus beta h cut omega from the denominator outside, so that in the if I'm taking it into a numerator, so this will become exponential beta h cut omega, and the denominator we will be left with exponential beta h cut omega minus 1. Okay, so that this is equal to e power beta h cut omega by 2 e power beta h cut omega by 2 upon e power beta h cut omega minus 1. Okay, so therefore option D is the correct option here. So let's continue with the next problem. The statement is, an ideal gas has a specific heat ratio Cp by Cv that is equal to 2. That is, it's given that Cp by Cv that is equal to 2. Starting at a temperature T1, the gas undergoes an isothermal compression to increase its density by a factor of 2. So the first step is, it is isothermal compression, so that the density increases by a factor of 2. So the initial density, let's it's 2 rho to 2 rho. Okay, and let's assume that the process stops at certain point A, so that because the isothermal process, the temperature will be same. Okay, so the second process is adiabatic compression. Okay, after this, an adiabatic compression increases its pressure by a factor of 2. So now the second step is adiabatic compression, adiabatic compression. Okay, where starting point and end point. Okay, so in the, let's say our starting point is A, P1 and corresponding temperature is T1. Okay, and let's assume that when process goes through adiabatic compression, so that the final pressure is P2 and the corresponding temperature is T2, and it's given that P2 is equal to twice the initial pressure, that is 2P1, or that is equal to 2P. Okay, if P1 is P. Okay, so that means here, because it's an adiabatic process, so we have to make use of the relationship that connect temperature and pressure. So the corresponding the relation is T power gamma P power 1 minus gamma, that is equal to constant. So this is a relationship that's valid for an adiabatic process and connecting temperature and pressure. Okay, so here for these two equilibrium states, I can write T2 power gamma P2 power 1 minus gamma, that is equal to T1 power gamma P1 power 1 minus gamma. Okay, so that means T2 can be written as T2, that is equal to P1 upon P2 power 1 minus gamma upon gamma multiplied by T1. So gamma is given as 2, that is Cp by Cb, it's given to us. So we are going to make use of this value. Okay, P1, that's P, that's the initial pressure, and P2 is twice the initial pressure, 2P, and then its power 1 minus 2 upon 2 and multiply by T1, which is T, you can say, or T1 you can say. Okay, that's the initial temperature. So this is equal to 1 by 2 power minus 2 and multiply by T1, or you can say T2 is equal to under root 2 times T1. Okay, so T2 is equal to under root 2 times T1. So therefore B is the correct option here. So this completes the solution for this year.